Namaste and welcome to this lecture on mathematical foundations for machine learning. In the last couple of classes we have studied the idea of continuous random variables and discrete random variables. We looked at probability mass function, probability density function, cumulative distribution function and everything, and we had a question to answer from the last class. The question was, look, I do not have my probability mass function or the probability density function or the cumulative distribution function, would I still be able to characterize this random variable? The example that we took was, look, I do not know what is the salary distribution of the salaried class in the city of Bangalore. Can I still get some representative number or a representative number which would tell that, okay, this is the salary of people, most likely salary of people working in Bangalore, and that is where we get into the idea of the expected values of a random variable and the averages and so on. So, we are just going to look at the expected values for discrete and continuous random variable, and then we are going to look at some important properties. So, I am going to look at this expected values of a random variable. I will side by side put both continuous and discrete, so that it becomes easy to understand. Okay. So, where do we start with? Note, first of all, note that the probability mass function or the PDF, the probability density function is a complete description, of the random variable of a discrete random variable or a continuous random variable and a continuous random variable respectively. I mean, what do we mean by this? Suppose you define an event, you will be able to get the probability of any event. So, this implies this: given an event, I can we can determine the probability of the event. Whatever that event that you have defined. So, once you find the probability of this event, now the next thing that starts is basically the interpretation and so on. Now, a simple example that we look at is, like, say for example, when students like apply for a job or probably a higher study somewhere, in their CV, if you see, they would typically include their academic performance in terms of one number, which is nothing but the cumulative grade point average, the CGPA. Now, what happens here? Now, suppose if it is an engineering degree, you typically take 8 semesters. There are 8 semesters in the engineering degree program, and every semester has a semester GPA, but when a student compiles a CV, he may or may not show the individual semester grade point averages. Instead, what he does is he just puts his single number, which you call as the cumulative grade point average. Now, this cumulative grade point average does not tell us anything about what are the semester grade point averages that the student has had. That means you really do not know the distribution of grades across the semester, but what comes to you is basically that one typical number which kind of captures all that you have done in the 8 semesters, and that one number is going to capture your performance, academic performance across your 8 semesters. we do not know the individual semester GPAs, but what we know is this one final number, which is the semester CGPA, the cumulative GPA, which is going to be some kind of what do you say, an average or some number which is going to reflect your academic performance. Now what had happened, we did not know, the student typically might not want to show his semester wise performance, instead he would capture this entire performance across semesters with only one number, which is your CGPA, right. Now in that case, like how do we, I mean this is another representation, or this is another way you characterize your random variable. Your semester, your academic grade that you have across the semesters is going to be, let us say grade point is going to be a random variable. You do not know what was your first semester, I mean we really do not want to tell us what is the, let us say the first semester GPA, second semester GPA and so on. But finally when somebody asks you, okay, what is your academic performance like, you say look, my CGPA is somewhere around 9 on a scale of 10. Now people try to interpret now, oh fine, this guy has got a 9 pointer on 10, which means he must be academically, whatever that is, right, academically excellent. So he has performed well, so probably the student is pretty good in academic activities. That is the interpretation that we have. So the question is, how do we find this one number, this one typical number? How is it going to, I mean how are we going to find out which is going to give some meaning about the data, give some information about the data, and that is exactly where we get into the idea of expected values of the random variable. So this expected value of random variable, there are two things that we have to do. See, expected value is calculated from the probability mass function and the probability density function, and the point is you may not have expected value to converge at all. It could be infinity also. There are certain cases, examples where we see this expected value would not even be a finite number, right. So we have certain problems with this expected value, but let us try to look at what it means. So let us look at this. So we have expected value of a random variable denoted as expected value of a random variable x is given by E of x is equal to sigma xi p x of xi, where I is equal to, let us say 1 to infinity 1 to n, say 1 to n. This is in the case of a discrete random variable. If the random variable is discrete, all you need to do is you get a weighted sum of the values that the random variable can take, where the weights would actually be the probability mass function or the probability mass associated with each of those values. In case of continuous random variable, this is going to be minus infinity to infinity x f x of x dx. It is going to be x f x of x, x into f integral x f x of x dx, where the integration limit is from minus infinity to infinity, or in whatever the interval that f x of x is defined. Okay, so some interesting points that we have here, we will say, I mean this is not something new. We will look at this discrete random variable expected value of x, we will look at it from something which we already have seen multiple times. We will come back to that in a bit of time, but we will just try to understand what could this expected value actually interpret to, right. So the first thing that we are going to say is expected value of the random variable is typically the, okay, this E of x is the average value of the outcomes, average value of the outcomes of a large number of experimental trials, of a large number of experimental trials. Right. It could also be this. We will see what this means in a bit of time. Expected value of x is also the best predictor of the outcome of an experiment. Right. It could also be this. Now, what is interesting is this formula, whatever we have seen, is not something new to us. Suppose I tell you, let us look at this. Suppose I tell you that x takes values, from the set let us say 1, 2, 3, 4, 5 and 6, right, and then I tell you find the average of x. Now, this is something which we all know. What is the average of x? It is basically 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, which is basically this number 3.5. Right. Let us look at this average of x in a bit more detail. So, it is going to be 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6, right. This is what we have. This is exactly the formula that we saw before. What was that? xi into p of xi, adding all of them. Here xi is basically the values 1 to 6 and each of them gets weighted by the probability, which is basically 1 by 6 that we have here. So, this is not something, the expected value of x is not something which we did not know, but we actually we have done it, but with what would you say, we basically did not pay much heed to it. We just said, okay, average, you take all the sum of all the numbers and then divide by the total number of numbers you have, and that gets you the average. Here if you actually see, each and every number basically gets weighted by the probability, from the probability of each of those numbers. So, that is exactly what we see here. So, E of x is nothing but sigma xi into p of xi. This is something which we see here. Okay. Now, what we do is we look at, so what does it mean? We have our PMF, we have this basically in the long run of repeated experiment, you will see that this this is going to be the long run average that you have, which is basically my expected value of x. So, this is what I have. Okay. Now, let us take one more thing. So, what we have done, we have taken expected value of x is nothing but xi, sigma xi into px of xi. Now, what we do is we remember we studied a couple of interesting random variables or distributions. We look at what are the expected values for each of those distributions. We will try to build it intuitively and then the mathematics would follow. So, let us see intuitively like what it is. So, I am going to look at the expected values of some discrete and continuous random variables. Right. So, what is that? The first one that we saw was Bernoulli random variable, where we said that x is distributed as Bernoulli with probability of success p. So, the probability mass function was PMF Px of x is equal to p if x is equal to 1 minus p if x is equal to 0. This is what we had. So, my expected value of x is nothing but sigma xi into p of px of xi. So, here I is equal to 0 to 1, we will say x I is equal to 0 to 1. So, what do I have? I have x is equal to 0. So, this is nothing but 0 into 1 minus p plus 1 into p. So, the expected value of Bernoulli random variable is basically the probability of success itself, right. Then if you look at binomial distribution, let us look at 2 expected value of binomial distribution. So, let us take x is binomial of p, binomial of n comma p, because binomial distribution requires the number of trials n and the probability of success p, and remember this probability of success p is going to remain the same across all the trials, and the trials are not going to, the outcomes of trials are not going to be influencing the outcomes of the other trials. So, this is what we have. Now, that means this is nothing but n independent and identically distributed Bernoulli trials, right. The key word is independent, that we are going to exploit now, distributed Bernoulli trials. So, what is it that we have? We say that okay, if in one trial we have a probability of success to be equal to p, in n trials the probability of success is going to be np. So, we are going to say in n trials the number of successes that you are going to have is n into p. So, we say that in one trial the expected value of x was equal to p corresponding to Bernoulli. Therefore, in n trials I will say n independent trials, of course in this case as far as the expected value is concerned it would not really matter because in variance this independence comes into picture. So, let us look at this in n independent trials we will have we can say this, we can have NP successes. What was binomial distribution trying to do? Binomial random variable was trying to look at the number of successes in n independent trials. So, if you have n independent trials, the average number of successes, the expected number of successes that you would get would be n into p, which is pretty straightforward. Now, in fact you can actually do the summation, we could probably leave that as an exercise to the participants. You can look at the summation, you know that the binomial distribution has the probability mass function which is n choose k p power k 1 minus p power n minus k and so on. So, you can actually do this and then prove that it is actually equal to n into p, right. The third one is more interesting. The third one we saw was geometric distribution. Geometric distribution, x is geometric of p is what we had. So, what are we looking for? What was the geometric distribution actually trying to do? The geometric distribution was trying to find out the probability of the first success in kth trial, right, given that the probability of success is let us say p and the probability of failure is 1 minus p and the trials are repeated till you get the first success. That is the key word there, till you get the first success you repeat. The question is, on an average how many trials should I do to register the first success? That is the question. So, the expected value of geometric distribution would precisely be looking at, it will look at the expected value of a geometric distribution tells you the average number of trials that you must conduct in order to get the first success. This is pretty interesting. Suppose if I tell you I have a fair coin where in which the probability of getting a head is half and probability of getting a tail is half. Now what I want to do is I want to find out, suppose I tell that the event of getting a head is success. So how many trials I must do at least to get one head, to get at least one head. I mean you may get it in the first, but you may actually not get it in the first also. You get a tail, and the second toss again you may get. So at least you must do 2 trials. That is exactly what we are looking at. So if the probability of getting a success is p, that means I say okay, let us look at this, then we will try to understand. Suppose I will give a specific example and then we will be able to understand. Suppose probability of success p is equal to 1 by 10. Now what do we understand from here? Probability of success being equal to p is equal to 1 by 10. What do we understand from here? In 10 trials you get one success, right. It takes 10 trials, I mean you get one success in 10 trials. Therefore if I want to see the first success, then on an average I must at least do 10 trials. That is what it means, right. So what is the expected number of trials that I need to register to conduct for getting the first success? It is basically 10 in this case, which is pretty simple. The 10 is nothing but when p is equal to 1 by 10, the expected value is going to be 1 by p, which is nothing but 1 by 10. So I must have 10 trials at least. So what we are going to do is we are going to say that expected value of x in case of geometric distribution is nothing but 1 by p. This is something which we should know. So E of x for a binomial distribution was NP, where n is the number of trials and p is the probability of success. For geometric distribution it says the expected value of number of trials, for you to get the first success is at least 1 by p, right. It is at least 1 by p, that is what it means. The fourth one, we looked at the equally likely distribution, which is what we started off this class with. Is that I have 6 numbers, I want to find out the average of these 6 numbers. It is basically add everything and divide by the number of numbers, which is equal to 6. So that gave you the expected value of this. Then we are going to look at Poisson distribution. You really do not have to worry because the average itself is a part of your PMF. So where lambda is there, that is the average arrival rate. So Poisson distribution, E of x is equal to lambda itself, right. E of x is equal to lambda itself. If you look at continuous distributions, if you look at continuous random variables, then it is going to be this continuous random variables. The first one that we looked at was x is uniformly distributed in the interval a comma b, right. We had this. So I want to figure out what is expected value of x, what is the expected value of x in this case. What is the expected value of x? We know that fx of x in this case is basically 1 by b minus a. So now what I want to do is I want to find out expected value of x, which is nothing but integral a to b x into fx of x dx, which is nothing but 1 by integral x into 1 by b minus a into dx, which is nothing but from a to b. So I have x squared by 2 into b minus a, and this is nothing but b square minus a square by 2 into b minus a, which is nothing but you have b minus a into b plus a. B minus a gets knocked off from the numerator and the denominator. So I have b plus a by 2. So the average is nothing but take the endpoints, add them and divide by 2, right. So that is what we have. The second one that we looked at was exponential distribution, x exponential distribution of, let us say, the parameter lambda. Now, in this case you would see that the in this case we would see that the exponential random variable, the average itself is equal to the lambda. So, this is nothing but the f(x) of x in this case was lambda e power minus lambda x. Therefore, E of x is nothing but integral 0 to infinity, because exponential distribution is defined for x greater than or equal to 0. So, we have the 0 to infinity, I have x into lambda e power minus lambda x dx. So, when we apply the properties of this integral, we basically get this, which is equal to, you say that this is equal to 1 by lambda. When you compute this integral, you basically get 1 by lambda. So, that is basically the that is basically the expected value of x. So, in this case expected value of x is equal to 1 by lambda. For Gaussian, the mean itself is given, it is basically mu. So, for Gaussian E of x is equal to mu, which is given. Now, as I said before, there may be some distributions where the value would not even converge, therefore, E of x may not even exist. So, what are the properties of this expected value? We will have to look at a few properties of the expected value. So, properties of E of x. The first one we have is basically this. What does actually the expected value mean? You must understand what is the meaning of this. You remember, in the case of discrete random variable, we said this is basically the mass concentrated, or the probability mass concentrated at each and every point xi, where xi is the set of values that the random variable can take. That means this expected value of x is going to be the center of mass. So, we are going to say that so basically E of x corresponds to the center of mass. This is basically the center of mass. In case of signals, if you see this expected value of x that you have, this would correspond to the DC value present in the signal, DC value in the signal. Suppose you have a voltage signal or a current signal where I mean you have some function. So, E of x would correspond to the DC amount, the amount of DC or the DC that is present in the signal. So, this is one important thing. Now, let us take this example where we had 1 to 6 and we said that look, the expected value of 1 to 6 was 3.5. If you look at it, x can take only values from 1 to 6, but then the average value says look, I am going to be 3.5, which is not even an element of this set, right. This is not even an element of this set. So, what we are going to do is we are going to say this E of x in E of x does not generally indicate the most probable value of the random variable. And you can have multiple PMFs to have the same expected value. So, which is like fine, okay. Now, one more thing that we want to do is we want to look at the most important property, which is the linearity property of the expected value. We are going to say that third one, E of Ax plus b is going to be A times E of x plus E of b, which is nothing but A times E of x plus b for A comma b scalars. The other interpretation that you can look at is, you can see this, we will take this case where we had this E of x is nothing but sigma xi p x of xi, this is what we had, I is equal to, let us say 1 to n, this is what we had. This is nothing but, suppose I take n values of x. So, I take that, since we have done linear algebra, I would just want to bring in that aspect of thing here. So, I want to write this as x1, x2, etc., xn. These are the values that this random variable x can take. So, x can take from this set x1, x2, xn. So, I am going to say x is going to be an n component vector, x is going to be, let us say in Rn, which is going to take values x1, x2, etc., xn, right. This is what we have. Therefore, what I would say is E of x is nothing but x transpose, let me put it this way, x transpose, or okay, the probability vector x transpose p x, I will call this as the probability vector, that is basically the dot product that I get p x. And if you see in the denominator, I can write this as 1, this 1 is nothing but I have the summation of all the probability values. So, for example, I will look at this, let us not get this, let us say just look at the average as such, since we have spoken about average, we will just look at the average once and then we will try to understand this better. So, suppose I say I want to look at the average of n numbers, which is x1 plus x2 plus etc. plus xn divided by n. I can write this as x1 into 1 plus etc. plus xn into 1 divided by 1 into 1 plus etc. plus 1 into 1 n times, right. Now, I can write this as, suppose I take this vector x vector to be, let us say x1 to xn, that means an n component vector. So, I can write this as the x vector transpose the 1 vector divided by 1 transpose 1 vector, is what I have, divided by 1 transpose 1 vector, right. I will put this as the vector. So, the average value is basically the projection of the data that you have along the axis, along the line where in which the coordinates are all equidistant from the origin. That means, all the points here in across all the axis you are going to see the value that it is going to take is 1, that means it is equidistant from the origin in all the directions. So, the average is going to be the projection of the data along the axis in which, along the line in which all the components are the same. So, this is what is the idea of average. One more thing that we were looking at was this average being the best predictor of the outcome of an experiment. So, average or the expected value of x is the best predictor of outcome of an experiment. We will just prove this. Right. So, this is what do you call it? This is something which we were actually looking at. Suppose if 2 cricket team captains are trying to toss, one fellow is going to toss and the second fellow is going to call out, that means he is going to predict what is going to be the outcome of that experiment, of that single toss. So, the thing is, I want to predict the outcome of an experiment before the trial is conducted, right. Before the trial is conducted, I want to predict what is the outcome of the experiment. So now what I have is, I will this idea of least squares which we studied, we are going to use that also here. So what we are going to say is, let us look at this. So let B denote the prediction that we have, let B denote the prediction, and we are going to look at the random variable x and let x be the random variable. What we want to do is, this B has to be close to the number, we need to choose, okay, we will do this. So we will do this, we say that we would like to choose B so that on an average it is close to the true outcome of the random variable x. Right. So this is what we have. So what do? We want to suppose if x takes the value x1, x2, xn. Now I want to find out what is the error in this, let us say, our prediction. So what we have is, we basically have this to predict the error. We have, okay, we use xi minus b, or let us say x minus b, let us say for where x is the outcome, okay. Now if I want to look at this x minus b, I want to look at the average of this. Now there is a problem that comes. You can have a positive set of positive excursions in the error, you can have negative set of excursions in the error. You could see that this positive excursion and the negative excursion getting cancelled out, and therefore you would say that, okay, there is no error at all. For example, I take this number, let us say 1, 2 and 3, the average is basically, my average is 2. Now what I do is I subtract this 2 from each of this, 1 minus 2, 2 minus 2 and 3 minus 2. Numbers I am going to get here are 1, minus 1, 0 and 1. Now what you do is, if you take the average of this deviations, this is going to result in 0, which says that there is no deviation at all. The average of the deviation is going to be 0, which says that there is no error at all. That is not something which we are looking for. So what we will do is, we will ensure that instead of looking at x minus b, we will ensure that you actually give you look at the error in a better way. So what we do is, I would probably look at x minus b the whole square, right. So x minus b the whole squared would be a better way to look at the error, and this is precisely what, and we want this squared error to be minimum. We want this squared error to be minimum. Now what does this mean? We want the minimum, what is that b which is going to minimize this? So we are going to say MSE, minimum square, minimize the mean squared error of b. This is basically, MSE is like mean squared error. So, we are going to look at minimum mean squared error. So, I am going to look at MSE of B is nothing but expected value of x minus b the whole squared. We said that expected value is I mean it is a linear operator that we are going to have. So, I am going to have x squared minus 2 x b plus b squared, which is nothing but expected value of x squared minus 2 b, b is the constant that you have, 2 b expected value of x plus expected value of b squared, and since b is a constant I am going to say expected value of b squared is equal to b squared itself. So, what we have? We have this, I have expected value of x squared minus 2 b times expected value of x plus b squared. Now, what we want is we want this minimum, this that we have mean squared error, this has to be minimum, and we want to find out that value of b which will minimize this. So, what I will do is I will say DMSE divided by dB, which is nothing but 2 e of x minus 2 e of x plus 2 b, and when I want to look at this as a minimum error I must equate this to 0. This implies b is equal to e of x. Now, I want to find out whether this is actually the minimum value. You take the second derivative test and actually prove that this value is 0, right. This value, I mean you see that the second derivative, let us look at this, d squared MSE divided by dB squared, which is nothing but this is going, that is going to be 2, this is greater than 0. Therefore, you say that the value of b, which is equal to e of x, minimizes the mean squared error, and that is precisely why we say that b is the best predictor for the random variable, right. So, we say that expected value of x, e of x is the best predictor best predictor of the outcome of a random experiment. Right. Okay. So, if you have studied the idea of expected value of x, now I mean that means we have studied the average, but there is a problem with this average. What is that? The expected value, if I just give you expected value, it is like your semester GPA, it is like your cumulative grade point average that we have. Now, what do we mean by this? This cumulative grade point average is no way going to tell me about the spread of the random variable. That means I do not really know what is the minimum value, what is the maximum value. Suppose if I say look, better example is look, let us say I have a startup company and I am saying look, I am going to hire an intern, there are only 2 people in the company, one is myself and the other one is let us say the intern, and I am going to tell you that the average salary that I am going to give is let us say 10 lakhs per year. Now, if I say 10 lakhs per year for the intern, he or she could actually think okay fine, I will also get 10 lakhs, but suppose if I say no, I will take 20 lakhs and I am just going to have you as a free intern, there is a problem there. The average is still 10 lakhs. Suppose I tell you no, I am going to take 10 lakhs for myself and I am going to give you 10 lakhs. Now, that means okay, the intern is going to get some money. Otherwise, I can say that look, instead of 20 lakhs, me taking 20 lakhs fully, let me take 18 lakhs for myself and then I give you let us say 2 lakhs. So, that is going to be the average is going to be 18 plus 2 lakhs divided by 2. So, you are going to get 10 lakhs again. So, these are all the possible combinations that you have. That means, when I tell you that the average value or the expected salary that you are going to get is 10 lakhs per annum, you always have to have a question, look, I must know what is the maximum and minimum salary, only then I can actually make a decision. How do we capture this? How do we find out what is the spread of this random variable? I must know what is the minimum and what is the maximum, I should know what is the spread of the random variable, and that is exactly where we get into the idea of variance of a random variable, which talks about the spread of the random variable helps you make a better decision, which helps you to understand the random variable better. So, you have a random variable where you do not know the distribution, you do not know the density function distribution CDF or whatever it is. Suppose if I give you just the expected value and the variance, we would still be able to get a rough picture of the random variable, and that is what and that is something which is commonly used. For example, if you look at Gaussian distribution, the mu corresponds to the expected value and sigma square corresponds to the variance of the random variable. Now, the moment I give this, I know almost pretty much about the spread of the random variable, how much is the distribution is, like how much is the spread and so on. So, what we will do is in the next class we will look at what is to say variance of x, and from variance of x we will build another idea of moments of the random variable. We will look at moments about the origin and moments about the mean, and with that this week's lecture will be over. In the next week's lecture we will start looking at multiple random variables, pairs of random variables and so on. There also we need to study some important ideas. We will look at that in the next week. If for the next class we will look at in detail about variance of the random variable. Namaste.